In this Statistics with Microsoft Excel, we look at measures of association. That is where we're going to compare the association between two categorical variables. Now, there are three measures of association for two binary categorical variables, and that is risk difference, relative risk, and the odds ratio. We've opened our spreadsheet, and as we can see, we have two variables. They are named exposure and disease. Now, do imagine that those are any two binary variables. Both of them have a sample space of two elements. They've got two levels, two categories. There are only two possible outcomes for each trial for each of these two variables. And we are imagining that the exposure happens before the disease. Now again, exposure disease, not the literal sense of the word. Any variable where you might consider the two possible values that variable can take for each trial is some kind of exposure. Maybe it is an active intervention versus a placebo. It does not matter as long as that is a binary variable. And then for the second variable disease, once again, not the literal sense of the word, that can be any kind of outcome for which we have a binary outcome. And we're going to call one of the outcomes the disease, the other one not the disease. And for exposure, we're going to call the two levels exposure and not exposure. As per usual, we're going to make a copy of all of this data. I'm just clicking in any one of these cells and I'm holding down Command or Control and hitting the A key. That selects everything. I'm going to hold down Command or Control and hit the C key for copy. I do see my marching ants. Let's open a brand new sheet. And I'm going to go to paste the values, and I see a copy. Let's do one more sheet. And again, I'm going to say paste, that little drop down, and say paste values. And I've got my copy. Let's rename these sheets. The first sheet I'll just call the copy. And do remember, I always do this such that I have a copy where I can make some changes to, but I always have that original right down there. Let's go to sheet number 2. I'm going to call this one MOA for measures of association. I'm going to select any one of the cells, hold down Command or Control and hit the A key. That selects everything. And then I'm going to go to Insert and hit the table button. My table does have headers. I'm going to click on that and then select OK. I've got a table. Now this is categorical variables. The way that we summarize this is through contingency tables. We want the frequencies. In this instance, we want the joint frequencies. So I'm going to select any one of the cells and I'm going to go to Insert and I'm going to hit Pivot Table. Because I was in one of the cells of my table will already have been selected for me. All I have to go down is say that I want my pivot table in an existing sheet. I'm going to click on that, hit this little selection button, and let's put this in cell number E1. Let's hit the expand button again and say OK. Now we've got two of these variables that we have to consider. I'm going to take my exposure. Remember I said this might happen before the outcome. That measurement is done, whether it's exposure or not exposure before the measurement is done for the disease. I'm going to take exposure and I'm going to drag that down into the rows column. I'm then going to take disease and drag it down into the columns section. And now look at our contingency table. Along the rows, I have my exposure and not exposure, the two levels for that variable. And along the columns, I have disease and not disease, or non-D. Now look along the rows. I have exposure, that's E, and not exposure, or non-E. And across the columns, I have my disease, and there I have my two levels, D and non-D, for the disease and not disease, or non-disease. And remember, those are just placeholder names for the two levels for each of these categorical variables. Now I want the frequencies. I can drag any of the two down into the values. So either exposure or disease, drag it down into values, and we can see the contingency table there. We see the four joint frequencies, 751, 7755, 623, and 7479, but we can also see the marginal totals and then the grand total. In our data set, we have 16,608 individuals. Now to save some time, I've already put four things that I want a calculation for. I want to set an alpha value, confidence level, a confidence coefficient, and we are going to have to make use of the natural logarithm. And the natural logarithm has a base of E, Euler's number, and we have to calculate that. So let's set our alpha value at 0.05. The confidence level is then equal to 1 minus the alpha value. So we want a 95% confidence level. Let's do our confidence coefficient. Now for each of these measures of association, we are going to make use of the standard normal distribution, the Z distribution. So to calculate this confidence interval, we're going to say equals norm dot INV. It's going to be 1 minus alpha divided by 2, so that we get to 0.975. Remember, mean of 0, standard deviation of 1. And we get to the very familiar 1.96 for our confidence coefficient. Now to calculate Euler's number, we're going to say equals EXP for exponent, and we're going to pass an argument or a parameter of 1 that says e to the power 1. Anything to the power 1 is just that number, and there we see Euler's number. It is an irrational number, and we see 2.71828, and it carries on forever and ever. Now for the risk difference and the relative risk or risk ratio, we need the probability of disease given exposure. I'll write it as such, and we also need probability of disease given non-exposure, and let's write it as such. Those are the two probabilities that I need. So let's try and calculate those. The probability of disease given exposure, that's going to equal, now there is my disease column, so it's either going to be 751 or 623, but I am conditioning upon only those that were exposed, so I'll have to look at that 8506. That was the number of people who were exposed. So it's going to be equal 751 divided by 8506. And I'm just clicking on those values. And there we see the conditional probability, the probability of disease given exposure. Now I want to compare that to the probability of disease for those that were not exposed. So that's going to equal, there's my disease column still, so it's going to be 623 out of the 8,102 that were not exposed. And we see the probability of disease given non-exposure. Now the risk difference is very simply the difference between those two probabilities. So the next four values that I want to calculate there is the risk difference, our margin of error around that risk difference, and then the lower and upper bounds for the 95% confidence interval. Now the risk difference is very simply the difference between our two probabilities. That's going to equal, I'm going to click on this probability of disease given exposure value minus, I'm going to click on the probability of disease given non-exposure, its value, and I see there it's 0.011. That is 1.1 percentage points, and I will say that the risk, now remember risk, probability, that means the same thing. Just two words that mean the same thing. In this instance, with measures of association, we use the term risk instead of probability. So I will conclude that the risk of disease is 1.1 percentage point higher in the exposed compared to the non-exposed. And I use the term percentage points because all I've done is I've taken the 0.011 and I've multiplied it by 100%. So I'd say 1.1 percentage points, and it's higher because it's positive. The probability of disease given exposure was higher than the probability of disease given non-exposure. So I say there's a 1.1% percentage point increase in the risk of disease comparing the exposed to the non-exposed. Now to calculate the margin of error, we need a few steps, and I'm going to do them one by one. The first thing that we might need is equal to the following. It is this probability of disease given exposure times 1 minus the probability of exposure divided by how many people were exposed. The next term is going to equal this probability of disease given non-exposure times, I'm going to use parentheses, 1 minus that value, close my parentheses, divided by the total number of people that were not exposed, that's the 8,102, and I get my second term. Now what I will also need is the square root of the sum of those two. So let's put it right there. That equals SQRT. I'll select that, open parentheses, it is that value, that term, plus that term, close my parentheses, and that is what I would need to calculate eventually my margin of error, which is going to equal the confidence coefficient times this square root that we've just calculated. And there I see my margin of error. So to calculate the lower bound, that's going to equal this risk difference minus the margin of error. And I'm going to say for the upper bound equals the risk difference plus my margin of error. And there we can see we are 95% confident that this increase in risk comparing the exposed to the non-exposed is between, that's 0.3 percentage points and 1.9 or say 2 percentage points. Now for a null hypothesis, there should be no difference in this risk. The risk of disease given exposure compared to those that were not exposed, that should be 0. And look at our intervals. 0 is not contained in that interval, and that would be rejecting the null hypothesis. And so we would say there is an association between these variables, exposure and disease. Depending on whether you were exposed or not exposed is going to determine whether you have the disease or not the disease. Now these are the next four values that I want to calculate. The risk ratio, its margin of error, and its 95% confidence intervals. Now the risk ratio or relative risk, that is not the difference between those two probabilities, but their ratio. So I'm going to say equal, I'm going to click on the value for probability of disease given exposure, / for divide by, and I'm going to click on the value for probability of disease given not exposure. So now we have a ratio. So to write a conclusion for this value, it is larger than 1, so we will subtract 1 from it. 1.148 minus 1 leaves us with 0.148. We'll multiply that by 100% to leave us with 14.8%. So we would conclude that the risk of disease is 14.8% higher comparing those that were exposed to those that were not exposed. If the value was less than 1, we would subtract it from 1. So 1 minus that value. Whatever remains, we'll multiply that by 100%, and then we would say there is such and such a percentage decrease in the risk of disease comparing the exposed to the not exposed. In this instance, we have a value that is more than 1 and we subtract 1 from it. Multiplying that by 100% leaves us with 14.8%. Now, to calculate the margin of error is actually quite involved. Here's the list of the numbers that we need, the frequencies that we need. Let's go through them. We need the frequency of the exposed and not diseased. So I'll go to my table. There's the exposed, there's not diseased, that's 7755. Let's go to exposed and disease, that's exposed and disease, that's the 751. Just the exposed, that will be 8506. The non-exposed and non-diseased, that's going to be the 7479. The non-exposed and disease, so non-exposed and disease, that's the 623. And then finally the frequency of the not exposed, that's 8102. Now I need to calculate a further two terms, and look how I do that. I'm going to say equal, that is the exposure and non-disease divided by, and then the product, so I'm going to put parentheses, the product of the exposure and disease times the number that were exposed. Close my parentheses, and I'm going to calculate the similar term down here that's going to equal the non-exposed and non-disease divided by, then the product, so I'm going to open parentheses, the non-exposed and disease times the non-exposed. Close my parentheses, and I get my second term. Now I need the sum of those two terms, so it's that value plus this value. And finally, we need the square root of this sum of terms. And now eventually we're ready to calculate our margin of error. That's going to equal this confidence coefficient times this final square root of terms. And we have our margin of error. Now, to calculate the lower bound and upper bound is also a bit involved. Unfortunately, we do not have a normal distribution of our risk ratio, and we have to take the log, the natural log of that risk ratio. Finally, we have to exponentiate. So we're going to say equal exp, open parentheses, then the log, open parentheses, that's going to be the log of this risk ratio that we calculated from our sample, comma, we have to tell it the base of the logarithm. So we're going to click on this Euler's number that we calculated before. We close our parentheses and we have to subtract our margin of error. Close the final parentheses, and there we have the lower bound. Then for the upper bound, we're going to exponentiate. So exp, what we want to exponentiate is the log of the risk ratio, the sample risk ratio, comma, it must be the natural log, so I've got to click on the value for the base, and then I'm going to add to that the margin of error, close my parentheses, and hit OK. And look at that. We have 95% confidence intervals. Now, under the null hypothesis, there should be no difference between the risk of disease given exposed and the risk of disease given non-exposed. That ratio should be 1. And we see that 1 is not within our confidence interval. And as with the risk difference, we would say we reject the null hypothesis, and these two variables, exposure and disease, are associated with each other. In actual fact, we see both values are greater than 1, so we would subtract 1 from it. And so for the lower bound, that would leave us with 1.037 minus 1. That leaves us with 0.37 times 100% leaves us with 3.7%. And for the upper bound, if we subtract 1 from that value, we get 0.27. We multiply that by 100%. That gives us 27%. So between 3.7 and 27.1%, that is the percentage higher risk of disease comparing the exposed to the not exposed. Next up, we go across to the odds ratio. Now remember, odds and probability are not the same. So let's calculate this. Now, to be able to calculate the odds ratio, we need our contingency table to be in a certain order. Now, of course, your variables are not going to be named exposure and disease, and certainly the two outcomes for each of these will not be exposure, not exposure, and disease, not disease. Those are placeholders. You choose, according to your research question, which one of your levels for exposure is E and which one for your disease variable is D. Given that, according to your research question, it has to be in this order, such that I can just very easily calculate the odds ratio. That's going to equal, I'm going to multiply along the main diagonal. So it's going to be the 751 times the 7479, divide by, and then I'm going to put parentheses because I'm going to multiply the cross diagonal. So 7755 times the 623. And that leaves me with the estimated odds ratio. It is 1.1625. That is higher than 1, so we would subtract 1 from it. Remember, under the null hypothesis, these two odds are the same. So the odds ratio would be 1. I see it's higher than 1. I'm going to subtract 1 from it, leaving me with 0.1625. I multiply that by 100%, and that leaves me with 16.3%. I would conclude that the odds of disease is 16.3% higher in the exposed compared to the non-exposed. Remember, if that value was less than 0, I would subtract it from 0. Now remember, if that value was less than 0, I would subtract it from 1, and whatever is left I would multiply by 100%, and I would say the odds are so many percentage points lower in the exposed compared to the non-exposed. Now we have to calculate the confidence intervals. For this we need a couple of values, and that's just going to equal 1 divided by each of the frequencies. So 1 divided by 651, I have that value. Next cell equals 1 divided by 7755. Next one equals 1 divided by 623. And then finally we'll say 1 divided by the 7479. So for each of my 4 joint frequencies. Next up, I want to sum over all those 4 values, and I'll just drag across all 4 of them, close my parentheses for the sum formula, and finally I want the square root, SQRT, of this sum of values. Now I can calculate my margin of error. That's going to equal the confidence coefficient value times this final square root value, and there I have my margin of error. Now once again, we have to say equals EXP. We're going to exponentiate. What we want is the log of this odds ratio, comma, remember we do need the base E, close parentheses, minus our margin of error, close parentheses, and then equals EXP, then the log, and it's the log of the odds ratio, comma, the base must be base E, close my parentheses, plus this margin of error. Hit return, and there we see our lower bound and our upper bound. Again, these values do not contain 1, which was the value under the null hypothesis, and again we can reject that null hypothesis, concluding that these two variables are associated with each other. In actual fact, we're going to subtract 1 from each, multiplied by 100%, so that would leave us with about 4%, up till 29, almost 30%. So that would be the confidence intervals for our odds ratio. And that is how we calculate the measures of association between two binary variables.